Hey, hi everyone. So today's problem session will focus on midterm review. But since there's a lot of topics to cover, in this problem session, I will focus on three main topics. The first one is conversion between luminosity, flux, and magnitudes. And the second one is the relation between angular size and linear size. And then the last part will be virial theorem and its applications. So let me write down. So again, I will explain the concepts in each part, but also I will show you some simple problems to let you know like how to apply these formula or theorem. But today I will not show you the detailed calculations, but I will show you the major steps, but I will give you the final answers and you can verify it by yourself later. Okay. Okay, so the first problem on luminosity, flux, and magnitude. So if we know that the sun have an effective surface temperature of about 6,000 Kelvin, and the radius of the sun, we know that it's about this number in kilometers. And so given these two conditions, we can calculate, first, we can know the solar luminosity. Okay, and also we can calculate the flux observed from Earth. And then we can also calculate the apparent and absolute magnitude of our sun if we know if we are using the Vega magnitude system and if we know the information of Vega. So so given some information of Vega, so if the luminosity, we know comparing to the sun, it is 40 times the solar luminosity. And the distance of Vega is also known. It's about 7.68 in parsec. Okay. Then what is the apparent magnitude? Of sun? And also what is the absolute magnitude? Okay, so let's start on the solar luminosity. So since the given conditions is the temperature, and the radius, right? So given the temperature, it is like straightforward to think of like the temperature is related to the sun's surface intensity by the Stephan-Boltzmann relation, right? So we can use that to relate with the sun's intensity, which I mean intensity, it means the luminosity distributed on the surface of the sun. So, okay. So for the first part, we want to know the solar luminosity. So this is our target. And if we relate with the Stephan-Boltzmann relation, we can write I equal L over 4 pi r squared, and that would equal to the Stephan-Boltzmann constant times the temperature to the fourth. Okay, so notice that this r over here is the radius of the sun. Okay, not the distance. Sometimes we will use L over 4 pi d squared, but that means we're consider the dimming of the object from the observed place. So the dimming is also it's also decaying with a surface of a sphere, right? So that's why it's the radius we need to use is the distance. But now we are considering the intensity on the surface of the sun. So we should use the radius of the sun here to relate with the Stephan-Boltzmann relation. Okay, so this one, and also remember that this thing is the energy flux, and by calling it energy flux, it means the unit is energy per time per area. Okay, so now with this equation, we can easily get the luminosity of the sun. So it's just 4 pi r of the sun squared times sigma t to the fourth, right? And if you plug in the numbers, you will get something like 3.8 times 10 to the 33 erg per second. Okay. All right, and then next, we can calculate the flux observed from Earth. Okay, so as I mentioned, if we are considering the flux observed from our place, then we are considering the dimming through the distance between us and the object, right? So in this case, we should use L over 4 pi d squared. So the flux of the sun should be its luminosity divided by 4 pi d squared. Okay. And let you know the difference. Okay, and that would be, since we already get the solar luminosity is just 4 pi r squared times sigma t to the fourth. All right, so we can write it out, and it's 4 pi d squared over here, and we can cancel out the 4 pi's, and then so we have the temperature, we have the radius, and we have the distance. Then we can be able to calculate the flux, and it's about 10 to the 6th erg per second per centimeter square. Okay, so because we know these are given in the question, and the distance we know, the Earth-Sun distance is just 1 AU, right? But remember, when you calculate these, make sure your unit system is consistent. So the numbers you plug in have to be the consistent unit system, so that you will get a correct answer. Okay. And next.
Just a quick question about units.
Yeah.
In the midterm, we have the choice of the units we will choose, or will there be like a unit imposed?
Sorry, could you repeat it? In the midterm?
For example, in the midterm, we'll have to choose the units we put in the end, or the units will be given. For example, the final answer.
Actually, I'm not so sure about this because I haven't seen the midterm problem.
Okay.
Right now, yeah, and I think it is like you're working the midterm problem on Canvas, but I'm not sure how Canvas works on units and how you enter the answers. Yeah, sorry, I don't know that, but you can ask Professor Sandstrom about this.
Okay.
Yeah. Okay, so now we are. Oh, okay. So now we are computing the apparent magnitude of the sun, and we will use the Vega magnitude system. All right. So let's write the information we have again. The luminosity of Vega is 40 times the solar luminosity, and the distance of Vega is 7.68 parsec. And we want to know the apparent magnitude of the sun. All right, so every time when you see magnitudes, just think of two equations. Okay, so the first one is when we compare between two magnitudes, we know there's a relation with the flux, right? So that's m1 minus m2, it's negative 2.5. log f1 over f2. Okay, and the second one is the distance modulus, which can also be derived from this first equation, but it is very useful. So the distance modulus is small m minus big M is 5 log distance minus 5. Okay. So these are the two equations related to magnitudes. But the difference is that the first equation, we are comparing two different objects with different flux. So compare two objects with different flux. But the second one, the distance modulus, is used to compare the same object. So the small m and big M is the magnitude of the same object. Okay, and the distance here, remember, it has to be in the units of parsec. So remember to convert your distance to parsec if you want to use the distance modulus. All right, so now we are computing the apparent magnitude of the sun, right? And previously we have already got the flux from the Earth and the luminosity of the sun. So since we already have the flux, it's pretty obvious that we should use the first equation. And also because we should compare the sun and the Vega, right? So we're comparing two different objects. That's why we're using the first one. Okay, so from the first equation, and we're comparing the sun and the Vega. So we'll take the apparent magnitude of the sun minus the Vega magnitude. That'll be equal to negative 2.5 log. Okay, so the numerator should be the flux of the sun. And that we know is the luminosity of the sun over 4 pi d squared, right? The distance of the sun. And this should be divided by the flux of Vega. And that's also L over 4 pi d squared. So since it's dividing, so L Vega in the denominator. All right, so let's see what information we have in this equation. So first, we use Vega system, Vega magnitude system. It means that the apparent magnitude of Vega is 0, right? Because that is the standard of this system. And then what else do we know? The distance of the sun and earth is simply 1 AU, right? And the distance of Vega is also given. This is 7.68 parsec. And the luminosity is given as 40 times the solar luminosity. Okay, so okay, remember, so the Vega distance is in parsec, and the sun-earth distance is 1 AU. So we should better convert 1 AU into parsec to match the distance unit in Vega. All right, so I won't calculate the details, but you can verify that from this equation, we would get the solar apparent magnitude of about negative 27. But okay, so this is already pretty close to the numbers on your textbook. I think it's negative 26.8. Okay, but the thing is that the actual magnitude of the star or the sun is actually varying with different bands. So we're actually not we're not specifying which band of the flux we're working on here. Okay, so just a note to remember that the actual magnitude would vary by band. Okay. All right, so now we have the apparent magnitude, and it would be straightforward to get the absolute magnitude. So now we want the big M. So we'll just apply the the distance modulus. So the apparent minus absolute is 5 log d, the sun, minus 5. All right, and again, this distance should be 1 AU, but converted to parsec. And then we already get this from the previous part. So we have the distance and the apparent magnitude. We should be able to get the absolute magnitude. So here you should get something like 6. Okay. But the standard number in V band is given as like 4.86. So just a reminder, so by converting 1 AU to parsec is actually pretty simple. So we know that 1 AU is 1 over 206,265 parsec, and that's 4.85 times 10 to the minus 6. And as I mentioned in the very first problem session, I think, this number is pretty worth memorizing, and I'll show you again in the next part. All right, so is there any question on this part?
Yeah, just a quick question. When we use the formula of comparison of magnitudes, would it change something if we put we reverse 1 and 2? Or do we always have to put, for example, like in this case, like the solar magnitude in the place of M1 and the Vega magnitude in the place of M2?
You mean if you can put like M mega as M1 and M sun as M2? Is that your question?
Yeah.
Yeah, of course you can, but well, you will get the same answers actually, so that's not a
Okay.
deal.
Okay.
Yeah.
Thank you.
Mm-hmm. Yeah, because
And then just
oh yeah. Please go
no,
ahead.
sorry, you can continue answering the question.
Yeah. Okay. I just want to mention that if you put like Vega as M1 and Sun as M2, then remember in the numerator of the right-hand side of that equation, then the order should revert
It will be
as well.
reversed.
Yeah, so
also.
that's why
Yeah.
you'll get the same.
Okay, thank you.
Yep. Okay.
I just want to confirm the distances have to be in parsecs when they're in the log form, right? Or do they just have to have the same units?
In the distance modulus, it has to be in parsec. That's because, yeah. But in the M1 minus M2, the magnitude flux relation, it doesn't have to be in parsec. You just have to make sure, because if you see this this equation over here, the distance, there are distance squared in both numerator and denominator, right? So they can actually, the units can be canceled out. So you just have to make sure the distance unit is consistent. But in the distance modulus here, you can see the distance is related to the magnitude. Yeah, and the number of magnitude, like the unit is already fixed, right? So for this formula, the distance have to be in parsec, or else it would be wrong. Does
Okay,
that
thank
help?
you.
Yeah. Okay. All right. So if there's no more questions, I will go on the relation of angular size and linear size. And for this part, I will use a simple example. So we want to calculate the angular size of both the sun and the moon as viewed from Earth. Okay. Okay, so to calculate the angular size, it's highly possible that we are using the small angle approximation. So basically, for objects that are far away, we can use this approximation. And basically, this means almost all astronomical objects. Yeah. Okay, so we will use small angle. Okay, so let me illustrate this a bit. So if this is our telescope on the Earth, and we are looking out the sky, and we see an object. Okay, so the size of this object is 2 times its radius, right? And if we look out, there will be an angle here. And let's say the object of this, the distance of this object is d. Okay, so with small angle approximation, we will get that 2r will be equal to d times theta, right? So that means theta is the angular size. So the angular size would be 2r over d. Okay, so it's pretty simple to calculate the angular size of objects on the sky. All right, so now we want to know the angular size of the sun and the moon. Okay, we have some information. So for the sun, we know we already used before, the radius is this much in kilometer, and the distance also in kilometer is 1.5 times 10 to the 8. All right, and for the moon, the radius is about 2,000 kilometer, and the distance is this much in kilometer. All right, so with these information, we can basically just plug in this angular formula, and then we will get the angular size of the sun. By plugging into r over d, we will get about 0.01. So the unit of r and d is both kilometer, right? So we have already made sure the unit is consistent and they will cancel out. So, so the unit of this angle we have now is in radian. Okay, and 0.01 radian, if we convert that to degrees, that is about 35 arc minute. Okay, you can also try this yourself. And if we calculate the angular size of the moon, you will also find that the 2r over d is also about 0.1 in radian, and that's also 35 arc minute. So what does this tell us? So it means that even though we know the size of the moon and the sun is like a huge difference, but as viewed from Earth, the angular size is basically similar. And that is why we can see total eclipse, right? Yeah, exactly. So this can tell us that total eclipse are possible. Okay, and so I just want to mention again the parallax, the parallax, because in parallax we can also use small angle approximation, and that's where we get the relation between, the conversion between parsec and AU. So I just mentioned before that 1 parsec is 206.265 AU, right? And we can see this in the parallax measurement. So we know that parallax means that we are measuring, so this is the sun, and the Earth is rotating the sun. Okay, and here is the Earth. So we can measure something, say a star far away, at like when the Earth is at this point. But like after half of the year, when Earth comes to the other side, we can measure again on the same stars. So then you can see that both of the measurements gives the viewing angle is different, right? And there will be an angle here. And the definition of parsec is just based on this parallax measurement. So it means if this star has a distance of 1 parsec, then it means the angle here will be 1 arcsecond. Okay. And since we already know that the Earth-Sun distance is 1 AU, okay, so we can focus on the triangle here. Then with the small angle approximation, we will get 1 AU is simply 1 parsec times 1 arcsecond. And since 1 arcsecond is 1/206,265 radian. So that's why we will get 1 parsec is this number of AU. Okay. And also, I mentioned in the first problem session that there is another very useful relation to memorize. So that is useful relation. That is, if we have an object at a certain a certain parsec, let's say d, because it's the distance, right? If we have an object at d parsec, then it means that for that object, 1 arcsecond, in our point of view, 1 arcsecond would correspond to the linear size of that object, that is dAU. So it means, let's say we have a galaxy at 10 megaparsec. Okay, so that means 10 to the 7th parsec, right? Then the 1 arcsecond angle we view will correspond to 10 to the 7th AU on that object. So this is very useful because so if we get data, any astronomical data, like for an object, if we know the distance of that object, then we can like quickly know the correspondent angular size to the linear size, because angular size is like we always need angular size on the observations, right? So if in a image or like data cube, the angular resolution is always in the form of angular size, and we want to convert that to physical size for a scientific purpose. All right, so that's all I want to say for the second part. Is there any questions? Okay, if no, I'll move on to the third part. Okay, so the third part is on the virial theorem and the mass density distribution or something like that. So so for applying the virial theorem, it's just a very simple equation that 2 times the kinetic energy should be equal to the negative potential energy, right? If the system is in virial equilibrium. All right. So to calculate this, we basically use the virial theorem from observed data. So if we have observations on the radial velocity dispersion, and the size, the core radius of the object, then we can easily use the virial equation. So I'll just simply write it out. So 2 times the kinetic energy, and the kinetic energy should be 3/2 m, the mass of the object, and sigma r squared. Okay, and this 3, the factor of 3 here is due to the assumption of isotropic motion. Okay, and that will equal to negative of the potential energy. And we will write the general form of the potential energy, which is gm squared over 2 eta times the core radius. Okay, so then we can use this to calculate the mass, because so one of the mass is cancelled out, and then we will get the 2 can be also cancelled out. So we will get a general form of the virial mass as 6 times eta sigma r squared times the core radius over g. Okay, so this is the general form of virial mass. Okay, so what does this mean? So in this equation, we can see that virial mass is basically dependent on this eta, the sigma r squared, and the radius, right? Okay, so even if this means that even if we have the same object with the same distance, same velocity dispersion, but if the density distribution is different, the virial mass calculated will also be different, because eta, we know that eta here is, it basically depends on the density profile of this object. So we can see that if you recall, in the last week problem session, we work on a homogeneous sphere with uniform density, right? So for rho of r equal constant, and that means a homogeneous sphere. So based on last week, we derived that the potential energy of the uniform density sphere is negative 3gm squared over 5r, right? And if we compare this with the general form of potential energy, which is gm squared, negative gm squared over 2 eta rc, then we will get that eta is 5/6, and which is about 0.8. Okay, so for a homogeneous sphere, the eta is about 0.8. Okay, so what about the Plummer sphere? So you already work on the Plummer sphere in previous homework problems, right? So Plummer sphere is another density distributions. You work in homework 3 and 4. And so the potential, you work on the potential energy and the density and the gravitational potential, right? So you went through this process and you get that eta is about 2.6. Okay, so you can see that for the same object, if the density, so the density distribution between a uniform density sphere and a Plummer sphere is very different. So the eta is also very different, right? So if we calculate the virial mass of the same object with these two different distributions, their mass will be like also a huge difference. So we can see the ratio of the mass calculated with Plummer sphere or the mass calculated with uniform density sphere, then since we're considering the same object, so the only factor that matters would be eta. So the mass ratio would be 2.6 over 0.8, and that's 3.2. So this means if the density distribution is polar sphere, then the mass would be 3 times larger than the uniform density assumptions. Okay, so this is a huge difference. Okay. All right, so that's all I want to say for virial theorem. So just make sure you're familiar with the process of, like, as I mentioned last week, from given the density distribution, you can calculate the gravitational force, and then the gravitational potential, and then gravitational potential energy, and then apply the virial theorem to get the mass or something related to the virial equilibrium. Okay, so any questions so far? So I will stay here through I will stay here through 8 p.m. Pacific time, and you can ask me any questions related on anything. And I won't have office hours tomorrow because of the midterm exam. So if you have questions, it would be better to ask me now. Yeah, okay. And I will also upload this note and the recordings today so that you have time to go through and prepare for the midterm.
Could you scroll back, please, to the question 2? I just wanted to make sure I jotted everything down.
Sure.
Okay, perfect. Thank you.
Could you please go back on the just there, yeah, on the equivalence between the between 1 arcsecond and the distance in AU?
Mm-hmm.
Like if we are given, for example, like could you please give back an example about it?
Okay, so I mean, okay, so if we look at this this diagram, this figure for the small angle approximation. So this figure is basically saying we are observing an astronomical object, right? So when we observe an object, there will be an angle, right, extending out through the object. And by the useful relation I mentioned, I say for any object at d parsec, then 1 arcsecond will be corresponding to dAU. And this means, okay, maybe I should draw another plot here. So let's say we are observing a galaxy. Okay, so let's say this is a galaxy. Okay, and we are observing from here. So again, there's an angle extending out through the object, right? Oops. Okay, so basically we are observing this object and we will get an angle over here. And if this object is at a distance of d and the unit is in parsec, then it means that, okay, so let's say the angle here, for this object, let's say the angle is 2 arcsec. Okay, so that means this, the diameter of this galaxy here corresponds to 2 arcsecond, right? For our observations. Okay, so this means that if we know this object, okay, let's use a real number. So let's say this object is 10 parsec away. Okay, d equal 10 parsec. So that means 1 arcsecond of this galaxy is equal to 10 AU. So that tells us that the radius of this galaxy is 10 AU.
Okay.
Does that make sense?
Get it. Because the diameter is 20 AU.
Yeah, because the diameter is corresponding to 2 arcsecond. So this is useful because like we usually, okay, so for example, if we're observing this galaxy and what we get is an image of this galaxy, right? So the astronomical data is like an image and we see a galaxy here and we know, and there is a pixel, right? So the pixel basically is the smallest angular resolution element. So if the angular resolution of our observation is, let's say, 1 arcsecond, then probably the pixel size here is 1 arcsecond. Okay, so on the image, we can see, oh, okay, the diameter of this galaxy is about 4 pixels, then that's probably 4 arcsecond. But what is 4 arcsecond in physical size?
It will depend on the distance. It will depend on the distance.
Yes, it would depend on the distance. So
and
that's why this relation is
okay, and we have a direct relation between the distance and the okay.
Yep.
So the angle is the angle of the diameter, it's not the angle of the radius. It's the angle of the whole object, right?
The angle of the diameter.
Theta is the angle between the if you go on the other side of the triangle, it's like the diameter is not the radius, right?
You mean this theta over here?
Yeah.
Yeah, this theta, like it depends. Like if you write a triangle like from here to here, then the angle would be 1 arcsecond, right? And that corresponds to the radius.
It would be, okay, it would be theta over 2.
Yeah. Like it could be anywhere. Like depends on like if let's say
it depends on what you want to look at.
Yeah. If there's a small star forming regions over here and I want to focus on just that star forming region, the angle will be different, right? And that corresponds to the star forming region size.
Okay, get it. Yeah. Thank you.
And the sketch that you drew is 10 AU. Is that the radius or the diameter?
10 AU is the radius. Yeah, because so I mentioned that the distance of this object is 10 parsec, right? So that means 1 arcsec equals to 10 AU. And we know that 1 arcsec in this plot corresponds to the radius. So that's why the radius is 10 AU.
Okay. All right. Thank you.
Yep.
Is it just like known that 1 arcsecond is equal to 1 AU?
1 arcsecond corresponds to okay, so I'm using the relation I mentioned here. that object at d parsec would means 1 arcsec corresponds to d AU. But that, okay, so 1 arcsecond is like not a fixed physical size. It will depend on the object's distance. If we look at a closer object, then you can see if the object is closer to us, the angle would be larger, right? The viewing
Yeah.
angle.
Oh, okay.
Yeah,
So,
but if
and
the
then,
object is, yeah,
so that distance measured in parsecs will then give you a size in AU.
in AU, like on that astronomical object.
Oh, okay, I get it. So the whole diameter would be 20, since it
20
covers a
AU.
distance of like 2.
Yeah.
Okay, thank you. Yeah, I didn't notice that line right there, so I was a little lost. Thank you.
Mhm.